video number 2. Hopefully you liked the first one, and in this one we're actually going to be getting down into actual reactions and mechanisms of a functional group called ethers. Alright, so this is probably going to be a little bit out of order. I think most organic professors usually talk about alcohols, and then after alcohols they talk about ethers and epoxides. I want to talk about ethers first, because there's less reactions with them, so I think it makes more sense to do, sort of the easier compound and then branch out into the compounds that can do a lot more fancy things. Okay, so this video is going to be about ethers. It might also be about epoxides. I'm going to see, I'm going to check the timer, and if the video starts to get probably a little bit longer than maybe an hour and a half, I'm probably going to cut it short and just make like a separate video talking about the other functional groups. But this one is going to be about ethers. So, first of all, what is an ether? So an ether is a carbon single bonded to oxygen, single bonded to another carbon. So the way that we would represent that in organic chemistry speak is that we would say it is R, O, R prime. Okay. So by the way, anytime you see in organic chemistry one of these R symbols, R just stands for, so it literally, the reason that it's R is that it actually stands for radical. Okay, but what it means is any carbon-based chain. Okay, so for instance, R could be equal to methyl or ethyl or propyl or isopropyl, etc., etc., etc. Okay, but an ether is just going to be ROR. Okay, oxygen that is single bonded to two different carbons. It can be the same carbon. You can have symmetrical ethers as well. Okay. So, for example, all of these would be examples of ethers. Right? So this would be an ether, this would be an ether, and this would be an ether. Hopefully you guys can all see sort of the general scheme of an ether. Like I said, it's just an oxygen that is bonded to two different carbon units. So this oh yeah, I got my stuff open. Sorry about that. It's just an oxygen bonded to two different things. I gotta be careful so I don't accidentally hit the rest of the screen with my hand like that. Right, but again, this oxygen right here is bonded to one carbon, two carbons. This oxygen right here is bonded to one carbon, two carbons. Alright, so that is what an ether literally is. Okay. So let's actually talk about some of the things that you can do with ethers. Okay, so I'll just call this like ether reactivity. Okay, so if you take an ether, right, take an ether like this, right. So one thing that you'll notice is that there are lone pairs, and I'm going to assume that you watched my last video, which I talked about how to identify a nucleophile, electrophile, all that good stuff. So you'll notice that there are lone pairs on an ether molecule, but one thing that I want you to be aware, and we do say, right, that lone pairs make something nucleophilic. However, the electronegativity of oxygen is pretty high. Not only that, but oxygen itself is fairly small in terms of atomic radius, okay? And obviously an ether is neutral. So even though there are lone pairs on an ether molecule, which does mean that those lone pairs are going to be nucleophilic, what we say is that ethers are very weakly nucleophilic. Okay, so they're very weakly nucleophilic at the oxygen. Okay, and again, if you watched my last video, you probably are well aware that I'm a big fan of molecular orbitals. So I always like to talk about things from a molecular orbital perspective. So remember, when we are describing nucleophiles, what we really mean is we're talking about the HOMO of something. So when I say that ethers are, oh shit, I said very nucleophilic. Very, sorry. They are very weakly nucleophilic. They are not very nucleophilic. They are very weakly nucleophilic at the oxygen, okay? And what we mean by that from a molecular orbital perspective is that the lone pairs in the oxygen sp3 orbitals, okay? And again, how did we know that those lone pairs were in the sp3 orbitals? Well, the oxygen itself is sp3 hybridized, which means everything has to be in an sp3 orbital, right? You only have 4 sp3 orbitals if you're sp3 hybridized. You don't have any p orbitals left over. So therefore, the oxygen lone pairs are in sp3 orbitals. So the lone pair of the oxygen sp3 orbitals are nucleophilic. And the lone pairs in the oxygen sp3 orbitals, that would be what the HOMO is. Okay. But again, this is very, very weak. And it's weak because the electronegativity of oxygen is high, so oxygen is not going to be super thrilled to share its lone pairs. And also, it's neutral, so there's really no sort of inherent driving force for oxygen to share those lone pairs. Okay. So let's talk about how ether does in terms of electronegativity. Or sorry, not electrophilicity. So, if you remember from the last video, in order for something to be electrophilic, we normally said that it either has to be a pi bond, like a carbon-oxygen pi bond or a carbon-nitrogen pi bond. Obviously, ethers have no pi bond, so that goes out the window. We also said that it could be something attached to a good leaving group, but oxygen and carbon, especially neutral oxygen and neutral carbon, are not good leaving groups. Or we said that it could be something connected to an atom that is formally positive, and again, ethers are not formally positive. So on their own, something like ether is weakly nucleophilic, but not electrophilic at all, on its own, all right? So maybe you're wondering, okay, you say, Brian, these aren't electrophilic at all, and they're very, very, very extremely weak nucleophiles. Why are we learning about them? And because, as you will see, even though they are not electrophilic on their own, the fact that ethers are weakly nucleophilic means that you can actually make them electrophilic if you react them with certain things. And so that's what we're going to talk about, and that's really what ethers are useful for. Let's talk about some of the reactions that you can do with ethers. Okay. Alright, so the first thing that you can do with ethers, okay, so if I have that molecule of ether, what I can do is I can react it with water and a very, very strong acid that does not have a nucleophilic counterion. So I'll do a little aside for right now so that you understand what I mean by that. So there's two types of strong, this is just my personal definition, but I want you guys to think about strong acids as being one of two types. Okay, so if you guys remember, the strong acids are like HCl, HI, HBr, NO3, H2SO4, technically also H3O+, but I'm not gonna write that one down. Also perchloric acid, but we don't really use perchloric acid in organic chemistry. These are the strong acids that I want you guys to think about. And these first three, these ones have a nucleophilic conjugate base, okay? Meaning that in HCl, right, the chloride minus anion is kind of nucleophilic. The bromide anion is actually pretty decently nucleophilic, and the iodide anion is extremely nucleophilic, right? Because iodine is negatively charged, it's huge, and if you actually look up the electronegativity of iodine, it's really not that large, even though it's a halogen. So something like this is actually pretty damn nucleophilic. Whereas these guys, when you do nitric acid and sulfuric acid, okay, so the nitrate anion looks like this. All right, and technically there's other lone pairs on the oxygens, I just didn't draw them. Remember, nitrogen and oxygen always will follow the octet rule, so if I ever draw a molecule with nitrogen and oxygen and it doesn't look like I'm satisfying the octet rule, I promise you I am. We just don't draw in usually the lone pairs on nitrogen and oxygen. I like to draw at least one lone pair if that lone pair is involved in something like a formal charge, just to sort of remind myself why that thing is there. Okay. So anyway, so the nitrate anion looks like that, and the sulfate anion looks like this. Okay. And one thing that I want you to just realize, you might not be able to see this right away, but neither the nitrate anion nor the sulfate anion is very nucleophilic. And I guess I could actually tell you why. Hopefully this doesn't take too long. The main reason why they're not nucleophilic is, hopefully you can see that both of them have a lot of resonance structure. Well, they don't have a lot of resonance structures, but nitrate has a resonance structure where the negative on the negative lone pair on the oxygen can delocalize into the double bonded oxygen. And the sulfate, the same thing can happen with the sulfate. And the sulfate can actually delocalize to the top oxygen or the bottom oxygen. So the sulfate has multiple good resonance structures. Okay. And one thing that I just want you guys to know, I probably should have mentioned this in my last video, but resonance is always going to decrease nucleophilicity. And that should make sense to you guys, because we know that resonance is a stabilizing force, right? Nucleophilicity. Forgot how to spell for a little bit. Okay. So resonance is going to decrease nucleophilicity. It decreases nucleophilicity because it stabilizes the electrons in a molecule. It spreads those electrons out. Okay. In order for something to be a nucleophile, you want the electrons to be relatively concentrated so that they can attack an electrophile, very, very rapidly. If the electrons are kind of diffuse and spread out all over the place, it's harder for them to organize and attack, some kind of vacant antibonding orbital. So resonance is always going to decrease nucleophilicity. So nitrate and sulfate are not very nucleophilic. And because of that, acids, strong acids like nitric acid and sulfuric acid, we're going to generally use them when we want something. So H2SO4, and H2SO4 is the really common one. We don't really use nitric acid that much in organic chemistry either. But H2SO4 and sometimes HNO3. Okay, in general, we're going to use these acids when we need strong acids, but don't also want strong nucleophiles. Okay. Because obviously if we use, something like HI is a very strong acid, but then by using HI we would generate I-, which is a really strong nucleophile. And sometimes we want to use an acid to make something acidic without accidentally or inadvertently introducing a strong nucleophile. Okay, so that was a little bit aside. I'm sorry. If we go back to what I talked about before, okay, what's going to happen when you react this ether with water and H2SO4 is that you are going to get two alcohols. Okay, so just like that. Alright? So let's talk about the mechanism for why that happens. Okay, so again, I just told you that if you have an ether and you react it with H2SO4 and water, you are going to get two separate alcohols. All right. So let's talk about why that is. We already know that an ether is very, very weakly nucleophilic at the oxygen. And sulfuric acid is a strong acid. And strong acids... Okay. So remember, strong acids are always going to be strong electrophiles. Okay? And if you don't realize that, remember one of the definitions I said for a good leaving group was anything, or sorry, one of the definitions for an electrophile was anything connected to a good leaving group, and one of the definitions of leaving group was the conjugate base of a strong acid. So you might have realized that basically by the transitive property, what that means is that all strong acids are good electrophiles, right? Because obviously this is the conjugate base of a strong acid, right? This is the conjugate base of sulfuric acid, all right? And therefore, anything connected to that, which this H is connected to that, would therefore be electrophilic, okay? And honestly, if that is too confusing to you, you can also remember one of the definitions of a strong acid is that they ionize completely into H+, and then, some kind of base minus afterwards. And obviously it should make sense that something like H+ is going to be electrophilic, right? It has a formal positive charge. H+ is literally a proton that's basically about the most electrophilic that you can possibly get. All right, that's like the definition of electrophilicity is a literal proton. All right, but we actually need to get talking about this mechanism. All right, so anyway, all strong acids are also strong electrophiles. So what's going to happen, right, is that this lone pair is going to attack the H, and that's going to go right there. All right, remember really quickly, right, from a molecular orbital perspective, right, there's going to be this right here is the O to H sigma, and therefore I have a nice big O to H sigma star right there. So the ether lone pair goes into the O to H sigma star. That causes the O to H sigma to break. All right. All right. So when you do that, you get this guy. And we know that oxygen, once it has 3 bonds, is formally positive, right? So now that gets me to here. And I now get, O. Okay. Right. So I generated that anion, and I also generated this species right here, right? So now, what I want you guys to realize is that this thing, right, for reasons that we already talked about, this is not nucleophilic, right? And 5 minutes ago, I kind of explained why that was not nucleophilic. So this is not going to react with anything. But remember, we do have water floating around, and it should make sense to you that water is nucleophilic. Water is going to be a weak nucleophile, right? Again, because it has lone pairs on the oxygen, but oxygen is pretty electronegative. It's pretty small, and obviously water is neutral. So water is a weak nucleophile, but it's still a nucleophile. And hopefully what you guys notice is that this oxygen on the ether is now formally positive. And one of the definitions of an electrophile that we gave is anything connected to something that is formally positive, which means that this carbon is now electrophilic, and this carbon is also now electrophilic. And so because both of those carbons are now electrophilic, the weakly nucleophilic water can attack that. Okay? So this can go there, which causes that to break, right? And that will get me to here. Oh, shit. I drew that wrong. That'll get me to here. So bam, and then O. plus. Alright, so hopefully you can see that it gets me there, alright? And then the final step of the reaction, almost always this is the final step of the reaction. Obviously, the product on the left is formally positive, and we don't really ever want to give a formally positive, reagent as an answer. So you have water floating around in solution. The water is probably just going to deprotonate that oxygen. Okay. And when the water deprotonates that oxygen, like in that mechanism, hopefully what you guys can see is that you are just going to get 2 molecules of alcohol. Alright? So we're going to do that mechanism a couple more times because I really, really want you guys to see it. And this time I'm just going to focus on the mechanism. I'm not going to talk about the molecular orbitals as much. Alright? But let's do a couple different ethers. So let's do, maybe something like... maybe something like that. Alright, so if we do this, and we react this with H2SO4 and water. Okay. So let's think about what we would get. Okay. So remember, the first step is the nucleophilic ether is going to attack the electrophilic strong acid. Okay. So nucleophile attacks electrophile, leaving group leaves. So that is going to convert my ether, which is normally not electrophilic at all. It's going to make my ether very, very electrophilic. And now, the water that's present in solution is going to attack it. Now, the products are going to be the same either way. From a mechanistic standpoint, hopefully what you guys maybe can see from this is that if the water attacks this electrophilic carbon, that's a tertiary carbon, whereas this one is a secondary carbon. Water is a weak nucleophile, and so this mechanistically is probably going to go, this one is a primary actually, and this one is a secondary carbon. Water is a weak nucleophile, so this is probably going to go via like an SN1 pathway. And so in an SN1 pathway, mechanistically, what's probably going to happen is that you're going to break off. Right, you're probably going to go in an SN1 pathway, so that's going to generate this thing, and then this thing, okay? And then, of course, right, the water can attack the carbocation electrophile right there. So those are my 2 products. Okay. And we'll do one more, just because I want you guys to see these mechanisms. Alright. Let's go. I don't know. Something fancy. Maybe like that. Who knows? With H2SO4 and water. Alright, again, hopefully you guys are getting the hang of this at this point, right? The ether is slightly nucleophilic, okay? It's going to grab the electrophilic H from sulfuric acid. When it does that, it's now positively charged, it's protonated, so that the water can then come in and attack one of the electrophilic centers. So in this case, it's probably going to attack this one. That's going to go there. And also, hopefully what you guys can see is that I am always going to put the formal charges, whenever I'm doing a mechanism, make sure you put formal charges in all of your intermediates. Alright? And then probably another molecule of water will deprotonate that. If you're asking me why it's a molecule of water that does that deprotonation rather than the sulfate anion that you got rid of before, the reason that it's probably the water that does that deprotonation, obviously, like, you would get like a nice, everything neutral if the sulfate deprotonated it, but it turns out if you actually look at the pKa, or rather the pKa prime, so the pKa prime of sulfate is actually greater than the pKa prime of water. And what that means is that water is actually a stronger base. Water is actually a stronger base than sulfate, which is kind of counterintuitive because water is neutral. So you would think that something that is like O- would be a stronger base than something that is O neutral, like water. But it turns out that this is technically a stronger base. Okay? And so neutral water will actually do that deprotonation faster than the sulfate anion will. Alright. So, let's see, we never did. So then that would get me to here. Alright. Perfect. Alright, so hopefully that makes sense. So that was the first reaction that we talked about. Okay, if I have a general ether, and it doesn't matter what those R groups are, they can be kind of whatever we want. Right. If I have an ether, and I react it with sulfuric acid and water, I can cleave that ether and instead generate 2 alcohols. Right? Okay, so that's the first thing that an ether can do. But now, let's see what would happen. Right? Let's see what would happen if, instead of using H2SO4 and water, let's see what would happen if I just used HX, okay, where X is equal to chlorine, bromine, or iodine. And in general, by the way, in organic chemistry, X pretty much always means a halogen. So chlorine, bromine, or iodine if you ever see HX. Right? So what that's going to do, all right, that's actually going to give you a mixture of the alcohol. It's going to give you a mixture of the alcohol plus the alkyl halide. Right. Now I drew it right now as putting the alcohol, coming from the left side of the ether and the alkyl halide on the right side of the ether. I'm going to teach you how to know if it's an unsymmetrical ether, how to figure out which side goes where. Okay. Because it turns out the way that I drew it, is actually, that would actually not happen in this case. So hold on really quick. But I'm going to teach you how to realize that. So this would actually be the OH, and the X would actually be over here. Alright? So that's what you get, and let's actually do the mechanism for this. So once again, okay, we know that ethers are nucleophilic, and we know that anything connected to a good leaving group is electrophilic. Bromine is a good leaving group, therefore the H is a good electrophile. So nucleophile attacks electrophile. I go into that nice HBr sigma star orbital, which causes the sigma to break. And that allows me to get to this guy right here. Alright. Now I have positively charged O, which means that both carbons connected to the positively charged O are electrophilic. But I have to be be really careful here. So the carbon on the left is definitely electrophilic, okay, and I can definitely do some kind of like SN2 chemistry with that. All right. So obviously, in the terminal part of step 1, right there, I got rid of Br minus. Okay. Now Br minus cannot attack this carbon right here. Because hopefully one thing you remember from Orgo 1 is that you cannot do an SN2 reaction on an sp2 hybridized carbon. SN2 reactions can only happen at sp3 centers, okay? And you also can't really do an SN1 reaction there either. And so what that means is that the bromine is only... Sorry, I could have just erased it. What that means is that the bromine is only actually available to attack this electrophilic carbon, which is going to allow me to get this product. Okay. Alright. So those are my two products. And again, those are my two products because, so just a heads up, this is incorrect, but I want to just show it to you anyway. Okay, the reason that that is the correct product is because this could not happen, right? So if I have bromide, bromide cannot attack that carbon because that carbon is sp2 hybridized. So this, if I drew, a mechanism that looks like this, okay, that mechanism would be incorrect. You're not allowed to do that, all right? Okay. And by the way, really quickly, you guys should understand why you're not allowed to do that. Because remember, in an SN2 reaction, this bromide ion, it's looking for the O to H, so let me get rid of that giant X, okay? In order for this sigma bond to break right here, that must mean that the bromide dumped into the carbon-oxygen sigma star. But where is the carbon-oxygen sigma star? I'm not going to redraw the whole molecule, but let's draw the bond in question, right? Remember, the sigma star orbital is on the outskirts, right? Oxygen is more electronegative than carbon, so the sigma star lobe of the oxygen is really small, and the sigma star lobe on the carbon is huge, but look where it is. The sigma star of this is literally like in the middle of the benzene ring. So there is no way in hell that this bromide anion is going to try to like weasel its way through a whole ass benzene ring to get to that sigma star orbital, right? It's going to collide. Remember, there's all of these electrons that are floating around this benzene ring. So that bromide is going to get so much repulsion, it's not even funny, right? So there's no way that that bromide can do that. And so that is why the products are these products that I drew in red, right? So again, let's do a couple more of those. Let's do, we'll do a symmetric ether this time, so I guess I'll do diisopropyl ether, right? And we'll react it with hydriodic acid and see what we get, right? So again, the very first step, nucleophilic oxygen ether is going to attack the electrophilic H of HI, and that is going to allow me to get to a protonated ether. Okay. Now, since both of the carbons on this protonated ether are well, actually, I guess my nucleophile is I minus, so I minus is really only going to do SN2. So then this I minus can then just do a nucleophilic attack on either of those electrophilic carbons, right? And you're going to get the same product regardless. And you're going to get this, and this, right? Okay. So we'll do maybe one more. So let's do. Okay, let's do that one, and we'll react this with HCl. So again, the first step of the reaction So that nucleophilic lone pair is going to attack the electrophilic H. Again, the H is electrophilic because it's connected to a good leaving group. So that is going to get me to here. Always draw in the formal charges of the intermediates. Okay. And again, we have to think a little bit. So chloride is negatively charged. That means chloride is going to prefer to do SN2 chemistry versus SN1. And so my two nucleophilic centers are this guy and this guy. But the one on the left is a tertiary electrophile, which SN2 is going to be really disfavored at tertiary centers. And so what that means is that the chloride is probably going to attack this carbon. And therefore my two products are going to be this plus this. Alright? So we're doing pretty good here. So remember, the first one we learned was that an ether with sulfuric acid and water will just give you two alcohols. And because it's two alcohols, you don't have to worry about the mechanism and whether it's SN1 or SN2. But if you have an ether and you use HX, then you're going to get one alcohol and one alkyl halide. And the alkyl halide, because it wants to do SN2 chemistry, the alkyl halide is always going to go on the part of the molecule that is actually receptive to an SN2 reaction, meaning it's going to go on the less substituted part of the molecule. Right? Alright, so now, hopefully maybe you can see the pattern here. So in the first reaction we generate two alcohols. In the second reaction we generate one alcohol and one alkyl halide. In the third reaction, you might be able to kind of guess where I'm going with this. In the third reaction, we actually generate just two alkyl halides, okay? And the way that we do that is we just use excess HX, alright? So the first part of the mechanism for that is exactly the same, because hopefully what you realize is that HX and HX are the same, alright? But we'll do it anyway, just to review. So if I have I'll do HBr. So nucleophile attacks electrophile, leaving group leaves, okay? That gets me to here, okay? And then bromine is a nucleophile. So bromine can attack either of the electrophilic carbons. It's symmetric, so in this case it doesn't matter. So it'll go, maybe there, alright? So that is going to get me to here and here, okay? But the really cool thing is that if you're undergoing, or if you're using excess HBr, hopefully what you realize is that this oxygen, just like an ether, this oxygen has a lone pair, and therefore this oxygen is going to be nucleophilic. And so if I have more HBr floating around, this oxygen is just as nucleophilic. Technically, this oxygen is more nucleophilic than the ether, for reasons that I will get into when I talk about alcohols. But this oxygen has a lone pair, just like the ether did, so it can act as a nucleophile. Nucleophile attacks electrophile, leaving group leaves. And that allows me to get to this species, which means, okay, remember, this oxygen is formally positive. That means that anything connected to it is electrophilic. So that carbon that I just put in pink is now electrophilic. And the bromide that I just got rid of can therefore attack that electrophile and expel that leaving group, allowing me to get a second equivalent of this bromide. Alright? So again, let's do another example of that. Okay. And let's do this one. Okay. By the way, just because this is a ring, please don't panic. The mechanism, I promise, is exactly the same. Alright, you're going to do the exact same stuff. Oxygen is nucleophilic. Oxygen attacks the electrophile, leaving group leaves. Okay. Make sure you draw in the formal charges. This means that now both of these carbons connected to the positive O are electrophilic. So the iodide that I just got rid of can attack one of them, leaving group leaves. Okay. So that now gets me down to here. Right? So hopefully you guys can see that. Right? But again, what we just talked about, right? This oxygen has a lone pair. That lone pair still exists. That lone pair is on an oxygen, which means it's weakly nucleophilic, but it's still nucleophilic. Okay? HI is a really, really strong acid. Therefore, it's a very, very good electrophile. So, nucleophile attacks electrophile, leaving group leaves. Okay. So that's going to get me to here. And then alright. And then the other I- that I got rid of in the previous step can then nucleophilically attack this carbon, which is electrophilic, again, because it's connected to that formal positive oxygen. And the final result would be this molecule. Alright? So again, it looks a little bit different because it was a cyclic ether, but you guys should all be able to derive this product if you know the mechanism. Alright? So hopefully that mechanism made sense to you. Alright? Alright. So, it turns out that those are there's a couple more reactions that ethers can do, but we were not really going to talk about them in this kind of undergrad Orgo 2 class. So those three are really the only things that an ether can do. All right. So again, if you have, so I'm going to make these non-symmetric so that it's easy to see. So the three reactions, right, that ethers can do, okay? So you can turn an ether into two separate alcohols. You can turn an ether into one alcohol and one alkyl chloride, or one alkyl halide, sorry. Or you can turn an ether into two alkyl halides. Okay? And the way that you do it for the first option is just H2SO4 and water. For the second option, you would just use a normal, like one equivalent or stoichiometric amounts of HX. And to do the last one, you would use HX, but you would just make sure you're using it in excess. Okay? Alright? And those are going to be the three things. Alright? And one other thing, again, I really just want to reiterate. So, because I talked about this a little bit, but I was doing the mechanism, and I think sometimes it can get a little bit confusing. Remember, if you have, there's certain ethers where you really have to pay attention to what the mechanism is going to be. So, if you have an ether like this, right, remember, this, the first step in all of these reactions is that you're going to protonate the ether. So, you're always going to wind up with a protonated ether, okay? And once you have a protonated ether, you have to really consider, obviously both of the carbons connected to it are going to be electrophilic. but you have to consider what substitution pattern those electrophiles are. So, like in this case, this carbon, this is going to be, well, this is actually going to be a methyl ether, and this one right here is going to be a tertiary. Okay, so this is a methyl electrophile. And this guy right here is a tertiary electrophile. So remember, when you're doing the mechanism, right, if you're dealing with neutral species, like water, right, you're dealing with neutral species like water, water is going to prefer to do an SN1 based mechanism. And we know that SN1 based mechanisms would prefer more substituted electrophiles. Okay. Okay. However, if you're doing something negatively charged, so like X minus, right? Negatively charged nucleophiles tend to prefer to do SN2 reactions, and obviously the SN2 is going to prefer the less substituted electrophiles. Okay. And so you have to be really careful. Obviously, if you're doing the first reaction or the third reaction, it doesn't really matter because you're going to get 2 OHs or 2 Xs. But when you're doing the second reaction, when you're turning an ether into, right, so when you're doing this guy right here, when you're turning an ether into an alcohol and an alkyl halide, you need to pay attention to the substitution pattern so that you know where the alcohol goes and where the alkyl halide goes. The alkyl halide is going to always, always, always wind up being, sort of from the less substituted part of the ether, right? Right, and we talked about that mechanism, so hopefully you guys understand why, all right? Perfect. All right, so we're only at 44 minutes, so I'll start talking about epoxides. I think I should be pretty good to go through it. Let me really quickly make sure that there's not something that I'm like really... Oh, well, I guess... yeah, I guess this technically isn't... this is sort of like a derivative of the first reaction, but one thing that you guys can think about doing... so remember the first reaction that I talked about... I don't know if you'll ever be, sort of tested on this, but the first reaction that I talked about was that if you add H2SO4 and water, you can just cleave this ether, and we did the mechanism for that. We know how this happens. Okay, if you need more practice, go ahead and do more practice. Okay? And if you really consider the mechanism for that, right? What you see is that, right, remember in the very first step, you generate a protonated ether. And then once you have a protonated ether, you have a nucleophilic species, right, a neutral. In this case, water is neutral, so it's going to follow an SN1 pathway. So in an SN1 pathway, the leaving group leaves first. And I'm going to generate this carbocation, and then this species right here. And then the water finally attacks in the last step. But one thing that I want you guys to realize here is that technically, right, this water attacking is the last step. And so really, you could have any nucleophile attack at this last step. All right? Well, okay, I take that. You can't have any nucleophile attack. But you could do a lot more than just water here. So, for instance, one of the things that you could do, so... I'll call this 1B. It's not really like a whole separate reaction because it's basically related to the first one, but it technically gives a different set of products. So if you have an ether like this one, and you react it, instead of H2SO4 and water, you react it with H2SO4 and some other alcohol. So let's say you react it with 1, 2, 3, 4. Let's go crazy. Let's react it with 1, 2, 3, 4. Let's react it with hexanol, right? Because we're feeling really cool, all right? If you react it with hexanol, hopefully what you guys see is that you can actually get some pretty cool stuff. You can actually get you would get this thing, all right? So And then 1, 2, 3, 4, 5, 6. So you would get that thing plus that. Alright? So let's do the mechanism so that you can see why you would get that. Alright? So again, right, if I have this, okay, we know that the ether is nucleophilic and it's going to attack the electrophilic hydrogen of sulfuric acid, and that's going to get me to here. Okay. Alright, I now have a primary electrophile right here, or sorry, a methyl electrophile right there, and a tertiary electrophile right there. Because my nucleophile is a molecule of hexanol, which is neutral, this is going to go via SN1 chemistry, so that means the leaving group is going to leave. And that's going to get me to this carbocation, and then that thing, and then of course the hexanol molecule, 1, 2, 3, 4, 5, 6, is nucleophilic, and it can therefore attack that electrophilic carbocation, which means that I'm going to get 1, 2, 3, 4, 5, 6. And then remember, in the final step, in this case, it's probably going to be a molecule of hexanol because I don't have water. But something would just deprotonate that molecule. So that my final product would be these two guys. Why is it not drawing? What the hell? Alright, sorry. Would be those two things, right? And again, I mean, you guys can get really, really creative, right? So, you know, you can use, obviously, we talked about using H2SO4 and water. You could also use H2SO4 and alcohols. If you wanted to get really technical, you know, you could start using nucleophiles even beyond, you know, just waters and alcohols. But waters and alcohols are going to be the most common ones, I think, right? So that's about all that I have to say about ethers. Okay, hopefully they made sense to you guys. And so the next class of functional groups that I want to talk to you guys about are epoxides. And I'm going to do my best to try to finish epoxides in this video. We're almost at an hour, so I'm not sure if I'm going to be able to do epoxides and alcohols, but I'm going to try to do epoxides. Alright, so let's talk about what epoxides are. So epoxides are three-membered. Epoxides are just three-membered cyclic ethers. Okay? So what do I mean by that? I mean that an epoxide looks like this, with two, there can be R groups coming off of the epoxide. Alright. But these are all examples of epoxides. So for example, you could literally just have the simplest epoxide, which might look like that. Like I said, you could have an epoxide where it's, you know, substituted like that. You know, who knows? Okay, right. So all of these examples would be examples of epoxides. All right. Cool. So now let's talk about an epoxide. So hopefully what you realize is that an epoxide is just an ether. So epoxides are going to behave almost identically to an ether, with one extremely important exception. So let's talk about the non-exceptions first. So from a nucleophilic perspective, the nucleophilicity of an epoxide, is roughly the same as an ether. If you want to get super technical, they're actually a little bit more nucleophilic than an ether, and the reason for that is because the lone pairs So because in an epoxide you're locked in a ring conformation, what that means is that these bonds, so like this bond and this bond, can't rotate. And because they can't rotate, these lone pairs are always locked, pointing in one direction. And because they're always pointing in the same direction, it's much easier for them to attack a random, passing by electrophile. All right. When you have an ether, something like this, right? This bond can rotate, and this bond can rotate, which means that these lone pairs, this lone pair and this lone pair, aren't really always pointing in the same direction. They're sort of constantly moving around, which makes it difficult to attack an electrophile, right? If you think about it, imagine you're, really, really, really hungry, and you're trying to, grab a burger, but there's like a puppet master controlling your hand, and your hand is like constantly flying all over the place, changing direction. You would probably have a hard time like grabbing a burger that was sitting on a table in front of you if your hand was constantly moving all over the place. But if your hand stayed still, it would be pretty easy for you to just grab the burger. You would just go up and, fucking grab it. I don't know. Hopefully that was a decent metaphor. It doesn't honestly really matter. That was probably beyond the scope of this class.